Forward here. Okay, so non-isothermal unsteady state operation. So when we first developed our material balances, we did derive the expressions based on unsteady state operation. So if you think back to your fundamental material balance, remember we had a form like this. Well, this one is more biased towards perfect mixing, but generally speaking, we had developed the equation using the unsteady state mode of operation. And then we did use steady state after that. So when it was appropriate to say steady state, then we said the accumulation term vanished and we carried on with that. Now we need to update that with the energy balance. So in our energy balance, we in fact did start with the unsteady state operation. When we first started deriving the energy balance, we did include the accumulation term, but somewhere along the way, we said for steady state operation, we neglected that term and we continued. So now we want to revisit that. And because we have a bit more experience with the energy balance now, we can expand on this term. So dE dt, we know how to express the energy in a system. We said that's in essence the moles times the enthalpy. Remember, that's molar enthalpy. So times the number of moles, that's the enthalpy of the system. And then you can also count up the pressure and volume. So this is in effect the hydrostatic energy of the system. So by virtue of the fact that there is non-zero pressure exerted within the reactor, you can think of this as the kind of hydrostatic energy in the system. And so if we are interested in the rate of change of the energy, given that the number of moles may be changing due to reaction, and the enthalpy is also generally changing because the temperature may be changing, then both these are temperature functions. And so when we differentiate this, we have to use our product rule for differentiation. So Ni dhi dt plus hi dni dt, right? And dni dt, of course, we know we can get that from our material balance. So for our reactor, we look up dn dt and we can substitute the expression there. So that takes care of that part. This part we know is this enthalpy can be expressed in terms of temperature. So we anticipate we'll see a dT type term over there. And then this dPV dt, if we know that the pressure is changing in the system, right? And for example, in gas phase reactions, the total pressure may be changing. So if you have a reaction where you are producing more moles than you are consuming, then the pressure will be rising. Also, even if it's a liquid phase reaction and your level was changing because your flow in minus your flow out was not balanced, then the volume may be changing with time. So we would also have to differentiate this for both terms. But of course, this is not what we've been focusing on. We haven't been focusing on pressure and volume change. Well, pressure a little bit, but this term is in a sense not the one we've been focusing on. We've been focusing more on the reaction itself and temperature changes due to reaction and so on. But this is our general updated energy balance now. So if we expand out for dE dt, so this is the general balance. We now know how to expand out for dE dt, and then we can rewrite the equation in that form. So that's our updated energy balance. And then in the case of the Cstr, of course, there's the balance. And then in the Cstr, we know this material balance applies. So as we said just now, we can substitute for dN dt over there. And then the equation looks like this, right? So you've gotten rid of a dN dt. You still have a dt dt, which is here, right? So you can repose this equation and you can do some grouping here, and basically you can get the equation in the form dt dt. So now you have the energy balance in the form of the rate of change of temperature. And of course, you still have the original material balance. So if you look back, we had derived the unsteady state version of the material balance like that. And so here, the new difficulty that arises is that the temperature is changing with time. So if we didn't have this energy balance, we would not know how to evaluate this reaction rate, right? Behind this reaction rate is the kinetic rate constant, and that rate constant depends on the temperature. So we have to solve these two equations simultaneously. So for every instant in time, you have a new temperature. You can use that temperature to recalculate your kinetic rate constant and hence your reaction rate. And by the same token, behind this Ni, right, to get the current number of moles of a component I, we do need to know the current conversion. And so we do need the material balance to solve this as well. Also, the reaction rate does occur here. So we do need the concentrations and so on for this reaction rate. So both these equations are tightly coupled to each other. You can't solve one without solving the other. So it's a pair of differential equations, or it depends on how many species you have to solve for here. But in terms of concept, it's a pair of equations, right? And so there's a nice example here with the Cstr where you can apply that and you can find how the concentration and temperature change with time. So in this case, this reaction is endothermic. So the temperature actually drops here. And so you find your reactant concentrations, right? So the blue and the green are the reactant concentrations, and C and D are the products. So those start to rise. But I think this reaction, yeah, it's not reversible, but the reaction rate does drop, right? So we reach a point where your temperature goes down. So it's endothermic. So your temperature does drop, which lowers the reaction rate. And then also your reactant concentration, you can see B goes from 200 to 50. So the concentrations have gone down, so the reaction rate has diminished. And then because now your reaction rate has gone down, your reactor starts to recover because your feed components are at a higher temperature. So you were feeding at a temperature of 350 Kelvin. So first, when the reaction rate was quite high, the reactor actually dropped below the feed temperature. But then when the reaction rate went much lower, then the contribution of the energy from the feed that raised the temperature again. So you can model these kind of transition events. You can simulate them. And all it takes is for us to update our energy balance. And that's, in essence, all you have to add to our unsteady state, to our energy balance. Okay, so work through that example. And yeah, there are some comments here about if the pressure is changing, how you would update the balance and so on. So using the ideal gas law. So if your pressure is low enough, you can use the ideal gas law to relate the rate of change of pressure to the rates of change in the total number of moles and the temperature. So all of that helps you develop your system. I've got some old code here. This is from MATLAB. So it's not in Python, but I think it is quite readable. It's similar enough to Python that you can adapt this quite easily. Okay, so play around with that simulation and see that all makes sense. Then in terms of our batch reactor, of course, we always wrote the batch reactor in the unsteady state sense for the material balance. Now for the energy balance, again, that dE dt term, we recognize E is mainly N and H, so we use the product rule and differentiate it out like that. In this case, we don't have flow terms, right? It's a batch reactor. So there's no flow in and flow out. The only heat exchanges with possible heating and cooling and shaft work. So the energy balance looks like this. And then, of course, we can expand out for dH/dt. So dH/dt, the rate of change of the molar enthalpy is, if you take heat capacity as approximately constant, then this is as simple as heat capacity times dt/dt. Right, so we now have a nice dt/dt appearing in our equation. And so we can substitute that. So this term, if we substitute that in here in our balance, then we only need to substitute for dN dt. And of course, dN dt we have from our material balance. So for the batch reactor, that's our material balance. So if we stick all that together, then we get finally this nice form for the batch reactor. So for our batch reactor, we can estimate the rate of change of temperature purely in terms of the reaction rate and the conversion and so on. So now we have, again, a dt/dt for our reactor, and we can solve that with our material balance, and we can find how the temperature and conversion change over time. If it's the case that we are not adding heat, so if the reactor is adiabatic, right? Adiabatic means we are not adding heat or removing heat from the reactor. So if it is adiabatic, then your dt/dt simplifies like this, right? In other words, we don't have a Q term anymore. So this is the general form of the energy balance for the batch reactor. If we are not adding or removing heat, Q vanishes. And then if we say shaft work is negligible as well, then we can set that to 0. And so the equation simplifies to this form. And then if you look at this and compare it with the material balance here, you can see that you've got a RAV over NA naught. So here you've got RAV over NA naught, right? So look here in the, so you've got RAV and NA naught here, which is the right-hand side of dx/dt. So you can actually rewrite this balance as the leftover terms times, sorry, not the leftover over here. You can substitute this RAV and NA naught by dx/dt. And so on the right-hand side, you can rewrite this as dx/dt times delta HR over this the sum here, this term or this factor. And then if you multiply both sides by this factor, then the balance becomes this. And if you look at this, you recognize that, well, you've got a derivative in time on both sides. So you might as well integrate with respect to time on both sides. And then you get a nice algebraic relationship. And actually, this is nothing but the adiabatic line that we've been using all these days, right? So that straight line that was crossing all the isorate lines, it's the same equation that we get here. So in a way, this is just giving us confirmation of the steady state balance that we already knew about. So for non-adiabatic reactors, we already did this. In the case of the Cstr, we had shown if your heating medium temperature is TA, then this is your overall rate of change of energy. Okay, and then for optimal temperature profiles in your batch reactor, of course, we had defined the ISO rate lines and the maximum rate path. And let's just get this up quickly. So in this case, we had our ISO rate lines. And we had so far talked about the CSTR and the PFR. We had not talked about the batch reactor, right? And now let's think about the batch reactor. So we are in a batch reactor now. And in this batch reactor, we are currently at some conversion. So for example, 20%, let's say our current conversion is 20% just arbitrarily choosing 20% here. So let's say 20% is there. Then what would be the best possible temperature for us? So let's say that's our 20%. I'm just moving my 20% to here, right? To here. So if you look at this line, you are currently at a conversion of 20%, and 20% is this line. Then where would be the ideal temperature for us to be at, right? So let's say we have the privilege of being able to instantaneously change the temperature in this batch reactor, right? And we would like to maximize the reaction rate. So what's the best temperature for us to use, for us to try to create in this reactor? Any takers on that one?
Oh, sorry.
Please go ahead.
I think it is the one that on the ISO curve, that say the line touches the tip of the ISO curve, or
so this point here.
Yes.
Yes, that's right. Thanks for that. So yes, as we know on these curves, if it's an exothermic reaction, this is the high rate curve. Then the curve here is much lower than that, and the curve there is even lower than that. So looking along this line, all points to the left of this point are at a lower rate. All points to the right of this curve are also at a lower rate. So this is indeed the highest rate point that we can get. Okay, and then if you take that further, and if you look at another conversion here, you can see the highest point is going to be there, and similarly the highest point is here, and so on. And so in the case of the batch reactor, our maximum rate line consists of these points. Well, it's the locus of these points. So this is our maximum rate path in the case of the batch reactor. And of course, we don't start on the maximum rate point. So for example, when we fire up this reactor, we start at some temperature T0. So let's say T0 is down here. And we know the tendency of our process, right? If we just leave the system to react by itself, it's going to do this. So we could simply let the system react, and then of course we don't want it to go all the way to equilibrium. So we would say, let it react to this point. And then we could say, from this point on, let's start applying cooling. So we could monitor this reactor and say, okay, when I reach this this conversion, let's say that 0.4, when I reach that conversion, then I need to start cooling my reactor, because if I don't do any cooling, it's just going to keep going along this line, and that's going into lower and lower rates. I do know this red line has nice high rates, so I'm going to cool such that I stay on this red line until I reach the desired conversion, which let's just arbitrarily say is here. Right? So that's where we want to stop. So that's one thing we can do. We can just let the system react until it reaches the maximum rate point, and then switch on a cooler. So we start passing cooling water into this reactor until we reach the desired conversion. So that's one thing we can do. On the other hand, we could say also, well, do I really need to wait until I get all the way there? Do I need to, can't I do something about the long wait I have until it reaches the maximum rate line? In other words, can't I get onto the maximum rate line even sooner? We know we will have to apply cooling here, but what about applying heating as well? So let's say we have another coil here. And the function of this coil is to do some heating for us. So if we apply heating, then fine, the system is always going to be reacting. So it's as long as we are underneath the equilibrium line, the tendency for conversion is to move upwards like that. So the system is always stepping up in that direction. And the temperature, the tendency also, if we leave it alone, is to increase. But possibly it's not increasing fast enough. It's increasing only along the adiabat. So remember, this is the adiabatic line. This is where we are not applying any heating or cooling. If we do apply heating now, then the temperature will rise much faster. And so the temperature might do something like this. So if we apply heating, then we can meet the maximum rate line even faster. And then we will, in effect, reduce the time taken to achieve this final conversion. And of course, the length of these lines don't relate to the time taken. The time taken derives from the values of the reaction rate that we go through. So if we manage to push ourselves onto the maximum rate line sooner, then we will progress faster. So we can save a lot of time by hopping onto the maximum rate line sooner. And because we have this nice plane of isorate lines, we can figure out exactly what, for example, steam flow rate to apply here. So let's say this heater was based on pulsing steam through this heating coil. Then in effect, the flow rate of steam, that's something we can control as a function of time. So we would say, until I reach this point, until I reach the maximum rate line, which is here, I'm going to force steam into my reactor. So we would use a high flow rate of steam. And then let's say the time that it took to reach here was this time, right? So we would force as high as possible a flow rate of steam. Then we reach the maximum rate point, and then we totally switch off the steam here. So no more steam, because now we are on the maximum rate line. And so now what we need to do is cool the system down. The system's tendency along the adiabat, so if we reach this point, the adiabat is here now. The system's tendency is to do this. The system's tendency is to increase in temperature. But if we are on the maximum rate path, we don't want the temperature to increase. So now we would tend to switch on the cooling coil. So we would be passing, for example, cooling water. So initially, we were not cooling. Initially, we wanted to raise the temperature. So we would have no cooling water. Then we would reach a point where we need some cooling water. And here we wouldn't use the maximum amount. We would use just enough cooling water that we stay on this line. Right, so that's the interesting stuff we can do in the batch reactor to navigate the plane. So if you like, this is an extreme form of control. This is an extreme way of navigating the plane, right? Up to now, we've done a kind of brutal navigation of the plane. It was get to maximum rate path, cool ourselves back down, then get back on again. So you can see the advantage of our batch reactor is that we can exert very fine control over the way this reactor operates. And that's why even though a batch reactor is kind of inconvenient, because you have to, every time you produce something, then you have to stop the reaction, you have to purge the reactor, recharge, do the next batch. It's kind of tedious, but you can do some very fine control in these types of reactors. That's why batch reactors are quite popular still in the pharmaceuticals industry. So for fine chemicals, for high value chemicals, your batch reactors are pretty good. They let you exert very nice fine control like that. Okay, any questions or comments there? And in the tutorial, there are new tutorial files in Dropbox. You've got some nice examples of that. There are some other nice case studies in the notes here. So also new sets of notes 0.08 unsteady state energy balance. Here's a real world case study where there was an explosion in a nitroaniline reactor. So this is orthochloronitroaniline, and then not aniline, yeah, this is orthochloro, yeah, okay. This is orthonitrochlorobenzene, the name is given there, and then it reacts with ammonia, and then we get our nitroaniline here. So it substitutes the chlorine, obviously, and you get this byproduct. So on balance, if you look at this, you actually have fewer moles, right? You've got 1 mole and 2 moles, so there's 3 moles here, and then you are getting 1 mole and 1 mole, so it's 2 moles. So 3 moles become 2 moles. So you might not necessarily think of this as, one of the things we look for is, do we create many more moles? And then you start to wonder about explosions. So in this case, you wouldn't have used moles to start wondering about explosions. But in this case, our reaction rate, the normal reaction rate is given by this. And on the day of the explosion, the reaction rate was actually a bit lower. But there was a period where the cooling water was reduced for some period. And what happened in addition was that the volume of the reactor was larger. So you had an unusually high loading of reactant. So because you had a high concentration of reactant, there was an unusually high, let's see, what was that? And your cooling was stopped for 10 minutes. And so the same energy balance was used in this analysis. So if you go back and have a look, it's the same energy balance that we've been discussing. So if you were to view this, your reaction rate was higher, so your conversion rate was overall much higher. What did I say? So if you had the same isothermal conditions, your conversion would have been lower. But in this case, because when we switched off the cooling, the reactor temperature ran away to a greater extent. So under normal conditions, when you don't have such a high concentration of reactant, if you were to switch off cooling for a while, you could switch it on again and it would go back to the normal operation. And if you recall yesterday with the R and G and the exceeding the ignition temperature, here on this day with the higher reaction volume, right, with the higher quantities, your temperature rose. And then when we switched the cooling back on again, this couldn't restore back to the normal levels. And so the temperature ran away in this exothermic reactor, and that caused the reactor failure and explosion there. Right, so I know I'm kind of waving my hand through this, but you can read all the details here. And so using the same energy balance, you can analyze for the situation where you can't restore your temperature back to normal levels. Okay, so that's one case study. Here's another case study where you have multiple reactions competing in the reactor. And so in this case, you have 2 of A giving us 1 of B, but then there's a series reaction where B converts to C as well. And so you've got 2 different sets of thermal dynamics. You've got a heat of reaction, which is, so this one is an exothermic reaction. So the first one is exothermic, and the second one is endothermic. And so you can imagine then that our energy balance is not going to, that our temperature can bounce around as we get the different quantities of these species. So in the first case, yeah, let's see here, we've got a, yeah, it's a semi-batch reactor, by the way, I forgot to say that. So this is a semi-batch reactor case where we are feeding A into the reactor as well. So in the semi-batch case, let's just save this quickly. So in the semi-batch case, we have, you can think of a batch reactor. And we know that one of the problems with the batch reactor is that as our reactant gets converted to product, the reaction rate goes down. But in a semi-batch reactor, we try to correct this by introducing a stream of reactant. So this stream is supposed to help us restore the concentration of reactants and maintain a good high rate. So in the semi-batch case, we do add a term for the feed of your component A as well. So for the semi-batch case, we have the concentration balance given like so, and we also have that the volume is going to change. So in this case, our reactor, it is a liquid volume reactor, and so that additional stream that is helping us restore the concentration, that is a liquid stream, and so our level is rising over time in this reactor, right? So the level is rising, and if our flow rate is constant, then it's simply rising like that, right? Now, in this case, we have an initial concentration which is lower than the feed concentration. So initially, your concentration of A is going to rise simply because you are feeding A into the reactor in that feed stream. So A concentration is rising, but the reaction is also proceeding. So component B is also being produced. And so as the concentration of A rises, then B gets produced faster and faster. So that's why the slope is not fixed here. You can see the concentration of B rising faster and faster. But there comes a point where the rate of A going to B is so high that your A consumption rate is not matched by the feed of A. So your A concentration starts to go down. So of course your reaction, your first reaction rate has gone down significantly. So then the B concentration, that would normally level off. But of course, B is converted to C as well. So as B is formed, B gets converted to C also. So you can see C starting to rise here. And then we reach a point where the first reaction is low now. So your production of B is low, but C is still being formed. So B is still being converted to C. So then C concentration keeps rising and B concentration keeps dropping. And then there comes a point where, well, the first reaction is not producing much more B, and then the concentration of B is low enough that the second reaction rate also suffers, and then the amount of C starts leveling off. And so if we think about the expected dynamics, we expect that where the first reaction, where that rate is high, that the temperature will start to rise because that's an exothermic reaction. And if we plot the temperature, yes, you can see that the temperature rises initially just because of that first reaction. And then as the second reaction starts to dominate, the second reaction being endothermic, then the temperature starts dropping over there. So all these case studies, they just help us illustrate that there is a close interaction between the reaction rate and the concentration and the temperature itself. You can't solve the one without the other. So even these curves are influenced by this temperature. So the way I described these curves was kind of independent, was that as if only due to changes in A, B, and C, these changes happened. But if you do fix the temperature, right? So if you rerun the simulation and you do fix the temperature, you'll see you won't get the same curves. And that's because when you take into account temperature, you find here that these curves shift significantly. So here, this temperature is changing by a very large extent, right? This is on the order of 160 degrees rise in temperature. So this reaction rate is really very high. And then when we reach this point, of course, it starts to drop again. And then that also contributes to the loss of the reaction rate here. And so the second reaction then is also influencing the shape of this curve and hence its own reaction rate. So all this is very strongly coupled, and you can't solve the one without the other. So that's why in the unsteady state balances, we have to combine both the material and the energy balances, right? And you can also simulate startup and shutdown of a CSTR. So we've been talking as if you can just run a CSTR and it will keep operating that way. But of course, in the real world, you have to start the reactor up, you have to shut it down. And so we have to model those situations. We have to be careful that we do end up in a good operating position. And so you can use the unsteady state balances to simulate the startup and shutdown. And there's another nice case study here, propylene glycol, and that's catalyzed by sulfuric acid. And you are given all the dynamics. You are given the heat of reaction and the kinetic rate constant. And the units are a little bit weird, but that's fine. And if you simulate this case, so in this case, we are given the feed rates and the starting amounts and all of that. So you can simulate these equations. So this being the, is this a CSTR? Yeah, startup and shutdown of a CSTR. So there's your balance. And then there's your energy balance as well. And then we can go ahead and we can simulate if we are doing this adiabatically or not adiabatically, if we are simulating the reactor temperature for one, and if we are also simulating the cooling water temperature exiting the reactor. So we are feeding in cooling water maybe intended at 25 degrees, but because it's an exothermic reaction, the cooling water will heat up and it will exit at these much higher temperatures. So that's how our energy balance looks. And of course, that's solved simultaneously with the material balance. And you find that, if you look at the relationship between temperature and concentration, so we are plotting this against time here. So as time is passing, our temperature is changing. So the left axis helps us look at the temperature. So we can see the temperature here. So this curve is temperature. So the temperature is rising and then it's settling down to the steady state. So that's the startup. It's going through these dynamics. It rises. It's an exothermic reaction. So the temperature rises, and then it reaches a point where the cooling water dominates, and so the temperature drops. Then the reaction rises in response, and then the cooling water, the flow rate increases again until that drops, and so it bounces around a bit until it settles down to a steady temperature. And then by the same token, the reaction rate was very high initially, right? That's why the temperature rose like that, because the reaction rate was so high. So, and it was also that we were simply feeding propylene oxide to the, let's see, propylene oxide. Yeah, we were feeding in our propylene oxide. So the concentration rose there. And with that, the reaction rate rose. But as let's see, as that happened, so this curve, of course, is talking about the propylene oxide concentration. So the concentration rose just because we were feeding it in. So then the rate was rising and the temperature was rising. Then because the rate was rising, the concentration of propylene oxide dropped. And so the reaction rate started to come under control. And then because we controlled the temperature and so on, then the rate restored. And so this bounced around a bit until it settled down to a steady state. And so you can plot the reaction rate as well. That's typically what we mean by production rate. And so if you try different starting temperatures, you'll find that there is an attractor steady state. So this system is quite stable. So remember, yesterday we made the distinction between stable steady states and unstable steady states. So in this case, no matter where you started, it would loop around. So it bounces around for a little bit, but then it settles into the steady temperature and concentration. So this is what we call let me just sketch something here. So this is a phase plot, and we construct a phase plot by taking the state variables. And so if we have, let's say with time, let's say we have the concentration, and let's say we have the temperature. So here I'm going to say this is concentration, this is temperature, and this is time. So this axis is time, and this is time. So we can imagine we have our concentration. So the concentration is changing over time in some way. And then the temperature is also changing in some other way. And that's fine. We know we can simulate it and we can get such curves, but we aren't exactly seeing the relationship between concentration and temperature like this. So instead of plotting it this way, what we do then is take a series of instants in time. So we just pick some time values and we look at both the concentration and the temperature. So if we read, for example, this point, then we can pick out a concentration value. So we can read up the concentration value at that time. We can also read up the temperature value at that time. And then on our plot here, if we plot this as concentration versus temperature, not versus time, then we can position the temperature here and the concentration there. And so that defines for us this point. So this point is what resulted from these 2 points. So we can read off the Y values for these 2 points on the time profiles, and then find where that point would sit on this CT plane. And then we can repeat that exercise. So we can pick another point. So at another instant in time, we can find another point. So let's say here, which has a concentration there, and let's say there, which has a temperature there, then that would be a point somewhere here, for instance. And so we can do that for all time. And so we can get the locus of points that describes for us how the concentration and time have changed. Sorry, how the concentration and temperature have changed. And that gives us a time-independent view of the relationship between these two. So these are the so-called phase planes, and we can use them to observe things like attractor points. So we could find that, okay, there's a point here where things spiral in, and they always seem to end up at that point. Then we can say there's an attractor there. So this plane is not a plane of functions. Remember, a function can't loop in on itself like this. So these are, this is a locus of points, right? All these lines, these curves here, are from loci of points. So that's a phase plane that helps us understand the dynamics of a system. So that's what has been constructed here. And we can see no matter where we start, the system loops in around and falls into this very stable, steady state. Okay. And then there's another example here, another unsteady state example. Right, so you have all the tools available. So namely your balances, you have those available. And also you are experienced with Python, so you can go ahead and simulate these and see if you can find some interesting dynamics features. Okay, any questions or comments there? Okay, then we have some tutorial problems on this. So on Friday, so somewhere Wednesday and Friday, we'll be looking at some examples on these. And we are going to move now on, just one second.